In this video, we're going to discuss Beer's law. Beer's law involves the absorption of light and why certain amounts of light are absorbed at different wavelengths, how intense that absorption is. There's an equation that says A, the absorbance, is equal to the concentration, the path length, and epsilon, the extinction coefficient. What's the idea here? I have a container and it's full of stuff. And I shine some light at it. Well, that light's going to pass through. If that light originally contains kind of all my colors, well, there's material inside. Depending on what that material is, it'll absorb some of those wavelengths. So we'll have some electrons sitting at some orbital, and they can pop up as they absorb a photon of the correct wavelength. As a result, only certain photons actually pass through the material. The others get absorbed along the way. Now, when a photon comes by and is absorbed, it's actually a very rare event. You have to have the angles just right. You have to have the photon hit the electron at the right moment in its oscillation, and there's a lot of complicating factors. Effectively, it's kind of a 1 in a million chance, but we're talking about mole scales. So a 1 in a million is 1 in 10 to the 6, and you've got 10 to the 23. It's happening a lot. But the effect is that it doesn't happen instantly. The reality is, if you've got a bunch of these red photons coming in, some of them stop early, some of them get in, and some of them actually do make it through. Just less. But if I had a longer container with more stuff, well, there's just more chances that it fails to make it all the way through. This is why the path length matters. How long your light is passing through your sample affects how many opportunities it has. Additionally, the concentration. Effectively, the two just work together. I have so many dots available for the light to run into here, so many atoms. I can either have a longer path to provide more atoms, or I can just have more stuff in the same path. The net result is, it's how many atoms is your light running into? How many tries does it have to be absorbed? So that's how your concentration and your length factor into how much light is absorbed. What we see is absorbance versus wavelength, and blue, green, yellow, red. If we assume our red is being absorbed, then what will happen is we'll have a very low blue, green, yellow, and it will shoot up over the red. Absorbance graphs show us what light is missing. So your sensor will have looked and said, hey, what's the number of photons I'm seeing at wavelength 400? What's the number of photons I'm seeing at wavelength 401, 402? It will find the original plot where it says, hey, here would be all of them. None of them are absorbed. And then for each one that we see less of, we move the line up and line up. And as we run out and we see less and less material, we grow a peak at that position. Well, this is based on wavelength. I've got my orbitals. Remember that my orbitals have a little variance. Even though this might be my n equals 1 and my n equals 2, there's some vibrational modes in here. There's even some rotational modes, and there's some up above. My electron could really be sitting in any of these, and it could jump up to any of these. And so there's a couple different transitions that are possible, each slightly more energy or slightly less energy than the other ones. And so there's a center peak and then a few peaks around it at higher or lower energy that's spread out, accounting for those slight variances. On top of that, you have the Doppler effect, spreading them out even a little bit more. And so we get these curves of absorbance. Nonetheless, some of these are more likely, and that is where extinction coefficient comes in. You are just more often than not likely to be in the lowest energy. Your electron is usually in the bottom. It's usually not in a higher vibration mode. It can be, but most of the time it's not. So you tend to have transitions that go from the bottom to various ones up above. This just gives you a preference in percentage, which is why some of our points are taller than the other. We don't have a straight line. It doesn't simply go over, straight up, and straight down. It's a curve. Every wavelength has a slightly different probability, and that is where our extinction coefficient comes in. It adjusts the absorption for how likely that wavelength is to have an absorption. The number of molecules you hit are controlled by the concentration and the length, and the percentage chance of each hit working is controlled by the extinction coefficient. Why this is useful is that, well, your intensity, how absorbent you are, is dependent on that concentration. So you can actually solve for how much material is in solution by knowing the extinction coefficients, knowing the path length, and knowing your absorbance. If you have a plot that is concentration versus absorbance for a material that you know, we'll say 1 molar, 2 molar, 3 molar, and you take a few samples. Well, double the concentration will double my absorbance. Triple the concentration will triple my absorbance. In the end, you get these nice linear graphs, at least if you haven't gotten so dark that almost no light gets through, or so pale that all of it gets through. But as long as you're in a reasonable range of concentrations, you'll get this nice linear graph, which means later, if you take a sample and it says, hey, it has an absorbance right here, but I don't know the concentration. All you have to do is plot it across until it hits, and go down and say, hey, your absorption would be what we would get if our concentration was, let's say, 2.2 molar. In fact, in Excel, if you have a series of data points, you can click on the data points, right-click, and you can do a linear regression. You can get a formula. You can see the R-squared values for how well it fits. Google Docs will do this as well. But you can get an equation for that line because there's a slope. This is a y equals mx plus b. B is our intercept. X is our concentration. M is the slope. This is what the graph is good for giving us. It tells us, hey, for each increase in concentration, what increase in absorbance do I expect? And Y is our absorbance. You can rearrange this. If you've done it for a calibration curve, now you can put in any Y value and solve for the X value. Beer's law is extremely useful in testing and materials like that. You can observe how much of various chemicals are there. And so anytime we do water purifications or water purity sampling, things like that, we tend to use a method like this. There's a lot of different methods to do it, just for fun. There's a few. Flame, ionization. Effectively, you have a burner with just fire, and you shoot a little stream of the water. And so you've got some water, you've got some whatever your ion is, calcium 2+, or maybe lead. You want to test for lead. But they hit here, and it just burns them. That very tiny stream is really a mist, incredibly fine mist. But it hits the flame, and it's so hot that it excites the electrons. And so wherever your electrons were on your lead 2+, they get excited. kind of like cranking electricity through them. You can do this with heat. They go up, and then they'll eventually go back down, and we have a sensor box over here that just watches for the wavelengths of light that hits it. And we get a little spectra for it, and we say, hey, I've got a peak here, and there's one here, and we can test lead-2, a pure sample of it, and we can figure out where its peaks would be, how intense they would be for a known concentration, and then we can say, hey, I did it with this other solution, and I got a spectra that looked like this. Well, that's about only 40% as tall, so it would be 40% as concentrated. And in doing so, we can figure out the concentration of lead. This is how we do a lot of water testing. Not just water, really anything. Flame ionization is nice and easy. There's a bunch of other ionization methods, plasma ionization, electrical arc ionization, plenty of ways to do it. But the idea is still the same. See the light that comes off? Because concentration affects the amount of the photons, it affects the emittance or the absorbance, and we can use that to compare to a known concentration to solve its unknown concentration.